Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the DC dynamic braking of induction motor. So, what we do to brake an induction motor, we apply DC in the stator, instead of AC we apply DC, and the motor gradually decelerates and come to 0 speed. Let us see how we achieve this DC dynamic braking of induction motor. Now, this is our circuit where we have two type of stator, a star connected stator. Now, in that case we have the stator is star connected. So, we remove the AC supply and apply DC in the stator, and we just use the two leads here A and B, and the C is left open. We do not apply anything to the phase C. Similarly, we can have another configuration. We can apply the voltage between phase A and phase B and C, and B and C are short circuited. This is the short circuited one, and we again apply a DC in the stator. Now, when we do that, what happens here is that we have a DC field produced. We have the number of turns in this case. So, phase A is producing an MMF like this, and phase B will produce an MMF like this. So, the resultant of these two MMF would be in this direction. The two MMFs will add off vectorially. So, if we add two DC MMF is a vector, the resultant will also be a vector. But however, this MMF or magnetomotive force is not rotating, there is no rotating field. So, what we have is a stationary field. Similarly, when we have 3 lead connection, this is where we have 3 lead connection A, B, C, all 3 leads are connected. Phase A will produce an MMF like this, phase B will produce an MMF which is along this axis, and phase C will produce an MMF which is along phase C axis. Now, if we add these 3 vectorially, what we will get, this is phase A MMF, phase B MMF, and we have phase C MMF, and when we add these two vectorially, when we get, what we get is a MMF which is along this axis. This is the resultant FR. FR is the resultant MMF. As we have before, we have FR here. Similarly, when you have 3 lead connection, we also have the resultant MMF which is FR. We can also have delta connected stator. It is a matter of arrangement of the phase connections. Now, when we have delta connected stator, we can have similar circuits. For 2 lead connection, we apply between phase A and phase B, and phase C is not connected anywhere. So, as a result, the current which is flowing like this would be here, and part of the current is here, and part of the current is here in this direction. So, the resultant of these 3 currents will be along AB axis. This is the resultant. Similarly, when we see the 3 lead connection, in the 3 lead connection also we have the structure like this. So, this is the current which is coming from the DC. Here we have the current coming from DC phase, and this has to come here. So, this phase BC is short circuited, phase BC will not carry any current, and hence the resultant of these two will be in this direction. This is the resultant MMF. Now, the motor is running, but the MMF is DC. So, what happens? We can understand that by drawing the equivalent circuit. let us draw the equivalent circuit of an induction motor under DC dynamic braking condition. So, what we have here is the following. We have the rotor circuit is here, we have the rotor reactance, the rotor resistance here, and then we have the stator, which is isolated from the rotor. So, we have the rotor circuit and we have the stator circuit, and here the motor speed is omega m. The motor speed is omega m. Omega m radian per second, let us say. Now, if we assume that when the motor is applied with a normal voltage, normal 3 phase voltage, that is the rotating field, and the rotating field will have a synchronous speed. The synchronous speed is omega ms. So, when we apply a normal 3 phase voltage to the stator, there is a rotating field. So, the rotating field has got the synchronous speed omega ms. This is the synchronous speed when a balanced AC voltage is applied in the 3 phase stator. So, under this condition, if the rotor is stationary, there is an induced EMF in the rotor, that is ER. So, we can say that ER is the standstill induced EMF when we apply a normal 3 phase voltage to the stator of an induction machine. So, we have ER is the induced EMF in the rotor in standstill condition. In standstill condition, when a normal 3 phase voltage is applied in the stator. Now, we must understand that when we apply a normal 3 phase voltage with respect to the standstill stator, the stator MMF is rotating at omega ms. So, the relative velocity between the stator MMF and the rotor is omega ms. Now, here what happens? We have applied a DC voltage. The DC voltage will produce a DC MMF, and the same induced EMF will be induced in the stator when the speed is omega ms. So, we can say that that is also equal to the induced EMF in the rotor under DC dynamic braking when an equivalent, we say an equivalent stationary field is produced by the stator. So, we can say that the induced EMF in rotor at under DC dynamic braking when an equivalent stationary field is produced by the stator and the rotor speed is not 0, rotor speed is omega ms. It means when the rotor is rotating at a speed of omega ms, because braking is initiated when the rotor is rotating. When the rotor is rotating at a speed of omega ms and we have a stationary field, again the relative speed between the MMF and the rotor is omega ms. What happens here is the following. We have the rotor here, rotor may be a cage rotor, and as we have already seen that we have a resultant field which is a DC field. Now, here the rotor is rotating at a speed which is omega m, and if omega m equal to omega ms, the relative velocity between the rotor and the MMF is stationary, is omega ms. So, that is basically will lead to the induced EMF, that is ER. Now, again if the rotor is rotating at a speed of omega m, which may not be equal to omega ms. So, what should be the induced EMF? If the rotor speed is omega m not equal to omega ms or less than omega ms, when the rotor speed is omega m less than omega ms, the induced EMF, the rotor induced EMF is equal to ER into omega m by omega ms. It is very natural. When we have a speed which is other than omega ms, when omega m equal to omega ms, the induced EMF is ER. When the speed is other than omega ms, less than omega ms, the speed is omega m into ER by omega ms. Now, this we can also rewrite as capital S into ER. Now, what is capital S? Where capital S is equal to omega m by omega ms. Now, we can also express capital S in the form of slip. We know that the slip of an induction machine is given as omega ms minus omega m by omega ms. Now, we can simplify this, that is equal to 1 minus omega m by omega ms, or we can readjust in this case omega m by omega ms is equal to 1 minus s, that equal to capital S. So, at any speed omega m, the induced EMF per phase, when we are talking about induced EMF, we are talking about per phase induced EMF. Per phase induced EMF of the rotor is capital S into ER. What about the frequency? The frequency is also naturally equal to S into ER, S into F, because the rate of change of flux linkage is happening at a frequency that is S into omega ms. So, in this case we can complete the circuit here. Here we have the induced EMF, that is E into ER into S, this is XR, the rotor reactance, but the frequency in this case is S into F, the frequency. So, this is S into XR, and we have the rotor resistance, that is equal to RR, and the rotor current here is IR. Induction machine is a rotating transformer. So, we have something like a transformer circuit. The primary is the stator induced EMF, which is E. So, this is E, the stator induced EMF. So, we rewrite this equivalent circuit. So, what we have got right now is an equivalent circuit which is of this sort. We have a transformer, ideal transformer here, and then we have reactance, we have resistance, RR, S into XR, and here S into ER, and the current here is the rotor current, that is IR. This is induced EMF, that is E. Now, maintaining the same current, what we do, we divide the voltage, the induced voltage as well as the impedances by S, capital S. So, if we do that without any change, we can say that this is our modified equivalent circuit. So, here we have ER here, same current IR, but we have changed this thing to XR because we have divided everything by capital S, by this capital S and this capital S, and then the resistance will be divided by capital S, which is RR by S. This is something similar to the rotor circuit of an induction machine, but here we have capital S, not small s. Now, again we refer everything to the primary side. When we refer everything in the primary side, so what we get here is, here we have E. So, we equalize the number of turns, this is E here, and this is the reflected current earlier, which is IR prime, same thing is reflected current here is IR prime, this is the stator. And we have the rotor circuit here. So, similarly, if we have the reflected current here is IR prime. Now, when we equalize the number of turns, we refer the parameter to the primary side just like a transformer. So, if we do that, we get the following equivalent circuit. So, we get the equivalent circuit which is of this nature. This is RR prime by S, this is XR prime, and here it is induced EMF is E. So, we have equalized the number of turns here. So, this is referred as XR prime. What is XR prime? XR prime is equal to A square into XR. What is A here? A is the turns ratio, A is given as the stator number of turns by the rotor number of turns per phase. Similarly, the resistance referred from the primary side is given as A square into RR, A is Ns by Nr. Also, we can say that the induced EMF E by ER is equal to Ns by Nr is equal to A. This is also a relationship between the induced EMF, which are proportional to the number of turns. Now, we have this equivalent circuit. Now, how is the stator current produced? We have this current here and this is the stator, and we have the rotor here. The stator is produced, if we take a simple 2 lead connection, the stator current is produced not by a 3-phase AC, but by a DC current. So, the stator current is produced by a circuit which is like this. If we take a 2 lead connection for a star connected stator, the stator current is produced by applying a DC voltage to the stator like this. So, this is our voltage Vd, and this is how the stator current is produced, this is Id. Now, the stator current in this equivalent circuit that we have already derived here is an AC current. This circuit is an AC equivalent circuit. So, we can say this is a AC equivalent circuit. But however, this is a DC circuit. So, we have to have relationship between the DC circuit and the AC circuit. So, what we do, we equate the MMFs, or we find out equivalent MMF what would be produced in case of a DC circuit. Now, let us equalize the MMF for DC and AC and derive the stator current in terms of the DC current. Now, when we take a AC circuit, equivalent AC current by equalizing MMF. So, let us draw a two lead connection for a star connected stator. So, we have a connection which is like this. And in this case, what we do here, we only apply the voltage between the two terminals, okay, maybe phase A and phase B here. Now, this voltage is V d, and the current which flows through the winding depends upon the winding resistance, and this is I d. Now, the number of turns here is N s per phase. So, each phase has got N s number of turns. So, what is the MMF produced here? The MMF produced here will be this MMF and this MMF. So, if we add the MMF vectorially, one MMF is here and the other MMF is here, and this MMF has a value that is N into I s, I d, N s into I d. This MMF is also having a value which is number of turns into the DC current. The resultant of these two MMF is the third side of the triangle which is here. Now, we have a triangle here and the third side of the triangle represents the resultant MMF. So, this angle is 120 degree, this is 120 degrees, because we have a 3 phase stator. So, what about FR? So, FR is calculated as N s into I d square plus each side is N s into I d. Here this is a isosceles triangle. So, this is N s into I d square minus 2 N s into I d into cos of angle between them, angle is 120 degrees under root. So, the resultant MMF is given as N s I d square plus N s I d square, and this is also N s, this also N s I d square here, N s I d square, because cos 120 is minus half. So, if you apply, if you substitute cos 120 as minus half, this will be N s into I d square under root. So, that is equal to root 3 N s into I d. Now, when we apply a normal 3 phase AC to the stator of an induction motor, each phase carries a current that is equal to I s. So, if we apply a normal 3 phase AC, what happens here? We have 3 phase stator in this case, and we apply a normal 3 phase AC. So, the currents are balanced current. We have phase A, phase B, phase C. Now, this current is taking I A, this is carrying current I B, and this is carrying current I C. Now, if the RMS value of this current is I s, I s is the RMS value. So, if the RMS value of the phase current is I s, the MMF which is produced by this is a rotating MMF. Here the MMF is rotating. So, the MMF which is produced here is not stationary, this is a rotating MMF, rotating at a speed of omega ms. So, this MMF which is produced here is also Fr or say Fs, the stator MMF. So, Fs is equal to the peak value of MMF is equal to 3 by 2 times into Ns into Is and peak value of the current Is into root 2. So, we have to equate this to MMFs. So, if we equate this, what we get here is root 3 Ns into Id, that is equal to 3 by 2 times root 2 Ns into Is. Now, if we equate this, what we get here is the following. This implies Is is equal to under root 2 by 3 into Id. So, this is an important derivation which we have for the DC dynamic braking. It means, if we excite the stator by means of a DC current, we get an equivalent AC current which is Is equal to under root 2 by 3 into Id. So, we use that AC current here. So, our stator is now an AC excitation. So, we have a AC excitation here and this is Is, and what we have here is a magnetizing branch, and this has got the magnetizing excitation or the magnetizing reactance is Xm, and we have the rotor leakage, that is Xr prime, and then we have the rotor resistance which is Rr prime by S. Now, this current is Ir prime which is going into the rotor. Now, the stator is excited by means of a AC current source. What is the torque equation here? Similarly, we can have the equation for the torque. Torque is given as 3 into Ir square Rr by capital S divided by omega ms, because we have an AC equivalent circuit. What is IR? We have a current divider circuit here. So, 3 by omega ms into Is is the current which is divided into two parts. This current is partly going here and partly going here. So, we have a current divider circuit, and the current IR prime is given as Is into Xm divided by the total impedance, in this case Rr by S whole square plus Xm plus Xr prime whole square, and since we have square here, so we get the following. This is Ir square, and into we have Rr by S. So, this is the equation for the torque production. Now, in this case, this torque is a braking torque, and S in this case is 1 minus small s. So, if we plot the torque speed characteristic here, so this is the torque speed characteristic, and this is our torque axis, and this is the speed axis. So, we have the braking torque, this is the torque which is negative. So, this torque will have the characteristic, this is our omega ms, let us say the normal synchronous speed. At omega ms, slip is equal to 0, but capital S is 1. At 0 speed, slip equal to 1, but capital S is equal to 0. So, the characteristic will be just opposite to a normal induction motor characteristic. So, this will start from this point and will have this nature. So, this is the characteristic under the braking condition. So, if we see here, we have the first quadrant, which is this is the first quadrant here, which is the motoring region, and the second quadrant is the braking region. Now, in this case, the torque is negative. So, if the motor was initially operated with some forward torque speed characteristic like this, and if at this speed we break it DC dynamically, the torque will be negative here. So, the motor will decelerate as per this torque speed characteristic, torque is negative. So, speed will come down and it will settle at 0. Now, one thing as we noted here, that at 0 speed the braking torque gradually vanishes. So, there is no possibility of speed becoming negative. Now, we can also increase the braking torque by inserting rotor resistance. So, this is for one value of rotor resistance. So, this is, let us say this is for RR 1 prime. Now, if you increase the rotor resistance, the peak torque remaining the same, we have increased value of braking torque. So, this is for a value which is RR 2. So, RR 2 is higher than RR 1 prime. So, this is only possible if we have a slip ring induction motor. So, we have seen how an induction motor can be braked with DC dynamic braking. What we do, we apply DC voltage in the stator, and the motor is allowed to brake from finite speed to 0 speed, and the braking torque becomes equal to 0 when speed equal to 0, and this is given by this torque speed characteristic which is in the second quadrant. So, with the discussion on DC dynamic braking, we stop for today's lecture. We will continue in the next lecture.